so we're going to start the session.
Wait, just give a minute to Chris to just broadcast.
Okay.
So you can change this, or you can just start with the housekeeping.
So this is a housekeeping item for folks that just came in. This is a live broadcasting on social media on both LinkedIn as well as YouTube. So when you're going in other room, please keep quiet. And also, if you do have questions, we do have a mini Q&A after each speaker session, and then we can have a longer Q&A session towards the end. And also, please raise your hands if any questions. Please help yourself with the snacks, pizza, drinks behind the room. Go. Okay. So we're gonna go live. So I guess good afternoon, good evening, and good morning, wherever you are. I'm your host, Bill Zhang. I'm a product manager from Cloudera, responsible for Iceberg. So today, and welcome to our Iceberg meetup today. So fantastic to see you guys in person. And also we have a lot of folks joining online as well. So we have tons of topic today, and just want to introduce the speaker here. So Vincent is one of the speakers who's going to present some of the Iceberg topics, and Sam from Netflix, and Vikram, he will join us momentarily, and myself, Bill, I will do a live demo as well. So Shaun will also share some of the customer story with you guys, and Win-Yu is going to do a demo as well. So this is just a topic here, right? Vincent is going to talk about the Apache Iceberg's foundation for Open Lakehouse. Shaun's going to talk about the customer use case. Terranet is our referenceable customer. And I'm going to do a demo and show 4 things. And also, Win-Yu is going to actually demonstrate the multi-function analytics demo with Apache Iceberg. And Sam is going to talk about REST catalog, very hot topic in the Apache community today. And also, Vikram is going to talk about incremental compaction using Apache Iceberg. With that, let me hand the floor to Vincent.
Thanks, Bill. Thank you, everyone, for joining today. Good evening, good afternoon, good morning for people here in the room joining us via web conference, YouTube, and LinkedIn around the globe. Thank you. So today, what we will go over is I will be presenting our journey with Iceberg, building an open lakehouse, how Iceberg is the foundation for our unified data layer to build this open lakehouse for our ecosystem and for our enterprise customers. All right, so when we look at the recent trends in the analytics, as we are looking at the explosion of data and growth, every business today is struggling to deal with the challenges of the data growth, the scale, the complexity that comes with it, and really having a hard time wrangling the data to make any meaningful insights out of the data. They're spending enormous amount of time in preparation of the data, cleansing, curation. We will see some of those challenges in the later slides, but that's what the scale of the growth, data growth comes in. They're also challenging to make any meaningful insights, for example, doing any real-time analytics, predictive analytics, detection and fraud prevention, and those business challenges that they're having. How do they make sense of customer sentiments to really look at how do I improve my product? What are the feedback we are getting from the product? With all the social media and analytics that you can do, how do you really find gold out of what you are getting out of these enormous, different, diverse source of data coming through? And then they're also having challenges with quality, compliance, regulatory compliance, and so on. So these are the big trends that are going in the analytics that are coming with the big challenges of data growth and the complexity that businesses face today. Let's look at briefly how the industry has been solving this problem. Even with the technology and solutions that we have today, how have they been solving this problem for a number of years now? So on the left-hand side, you have a variety of data sources that you can get the data from and into the system where you need to go through staging to clean, prep, transform, map those data into unifying them, and then making some meaningful data out of it and ingesting into the data warehouse. The data can be different types. It could be structured, unstructured, streaming, text files, social media analytics, whatever that you could get, or IoT, time series data, anything that you can get out of the and from the field or from the edge. And you got to stage into that and then put it into a warehouse, and then you can do now BI analytical queries and reporting on that. But that is way too much data. As the data really evolves and grows, the exponential growth of data is making it much more challenging to really make anything meaningful out of it. So businesses then say, well, let's say segmentation. Let's take the data and then let's say I'm going to, for each business unit, let's create segmentation as a data mart. And then so we can have much more finer control, much more sophisticated analysis that is targeted for that particular business unit, but to make sense out of it. That's where the data mart. But all of this really explodes the complexity and then starts proliferating number of duplicate copies of the data. And in addition to that, you got to be constantly doing ETLs from one system to the other system. Always you are spending most of the time in data preparation, data movement, and then synchronization, ensuring data consistency. These are the big challenges that industry faces today. What we see in the diagram is just probably 1/10 of the real world problem, real world deployment. If you really look at any enterprise grade, this could be 10 times much more complex in the real world systems. And to add to the complexity, each of the business unit will be basically using their own solutions, their own softwares, their own products, vendors that they would like to use. Now, the data between these data marts or data between these systems are not compatible. So even if you wanted to join data and do any aggregation and any meaningful reporting across these systems, you have to do a federated queries. And that is not faster compared to a native data system that you can actually make any meaningful reporting and analytics on it. So how does this problem get solved? And that's where the Iceberg really comes into picture. So Iceberg really solves this, eliminating all the silos that today industry has been struggling with for decades. It eliminates all the silos by unifying the data into an open data table format. And once the table format is all ingested into this Iceberg and data is ingested into the Iceberg, now any compute engine that can understand Iceberg table format can now leverage it. So you have one data set that goes through cleansing, curation, preparation into a unified data lake that any compute engine that wants to access the data, make any meaningful insights and reports and analytics can benefit from that. That's how the unifying of your data set and data lake really comes into more powerful competitive advantage for businesses today. All right, so let's look at Cloudera and Iceberg integration. So Cloudera, as you know, that it is a very big, strong open source company to the core. And we basically contribute to a wide array of open source projects and deliver open source products and very closely engage with the community, collaborate, innovate, and deliver solutions to the open source community. Cloudera is a big data company with hybrid solutions, hybrid cloud solutions, and we are solving with our ecosystem and Cloudera data platform, we are solving a very large, complex data management challenges that our mission critical enterprise businesses face today. At Cloudera, we are managing 1 zettabyte of data, both on-prem and on cloud. And we are standardizing on Iceberg as our new table format across the board, across all our form factors. We are expecting in 3 to 5 years, all of this data will slowly migrate over to Iceberg eventually. And that's where we are going to be unifying our open Lakehouse solutions. And then quickly, just wanted to highlight some of the community engagement and contribution our awesome engineering team has been doing over a number of years. And now that we have been integrating and adopting Iceberg, what are some of the key contributions that the team from Cloudera has been engaged and delivering to the community? Number one, we are actually stabilizing and helping improve and mature the open source Apache Iceberg. We do that by basically running much more focused, targeted, real world influenced workloads and increasing complexity, increasing mixed workloads with update and deletes, and how would our real-world customers that are doing businesses today, when they migrate to Iceberg, what kind of problems, what kind of use cases do they have? And we are evaluating and improving, identifying and improving and enhancing Iceberg. One key aspect that we delivered, one of the key features we delivered was Iceberg manifest caching, which we found that significantly regressed our performance, especially with BI queries. And we had actually built and enhanced and implemented the manifest caching to the Iceberg file IO layer. I'll talk about that, some of the details of manifest caching. And we have also implemented and support for Iceberg in Hive, Impala, and NiFi, and also stabilized the Iceberg functionality in Spark and Flink. The open source community has been doing a number of improvements in Spark, and we are very thankful to that. We appreciate that. And in our pod, we have been delivering some number of fixes that we have found for issues. We're also integrating and standardizing HMS Metastore across all our compute engines to make it as a one standard unified catalog for all our compute engines within Cloudera data platform. And also we have been contributing to the documentation in the available that is in the upstream. And we are doing a lot of evangelism through ApacheCon, presentations at ApacheCon, Future of Data Meetup like this one, and other forums, writing blogs and publishing demos and other articles. We also have periodic interlock with the Iceberg community and contributors to closely collaborate and work on more innovative solutions to make Iceberg more enterprise-grade solution. Right, so let's talk about Cloudera data platform and Iceberg integration. So we have enhanced our compute engines and solutions, CDW, CDE, CML, and CDF. So this is our data warehouse, data engineering, and machine learning, and data flow to support Iceberg V1 and V2 format. We're also supporting Iceberg table insert, update, delete in Hive and Spark engine. Currently, we are only supporting reads from the Impala engine, but in future, we will support updates through Impala engine as well. We have supported Iceberg V2, which means we are supporting row level update and delete support, positional deletes only. Our writes are defaulting to MOR, which basically produces positional delete files. And this one item, the next item is very key, that we are the only one who is basically now leading and implementing a materialized view support on Iceberg, which will be delivering a native Iceberg table materialized view to further accelerate BI and reporting queries. We're also supporting both Parquet and ORC file format with Iceberg. And some of the future items are, we will support equality deletes in future and support for copy on write across engines. And so based on the use cases, customers and applications can choose whether to do MOR, which is merge on read, or copy on write. And as I mentioned, that we will also support writes from Impala to Iceberg tables. In addition to that, we are also supporting all the key capabilities of Iceberg, like time travel, rollback, in-place table migration, and we extended query and DML supports for Iceberg table maintenance. And the next thing is very key, that we are actually implementing one common solution through our SDX integration to provide security and governance. So solutions and businesses today, they have different solutions for different systems to do security, authorization, and governance, and finer granular control, access control. But what we have done is that we have basically brought in our SGX integration on top of Iceberg to provide one uniform solution for governance and security. They're also doing a number of targeted workloads to further evaluate the functional performance and capabilities of Iceberg, where we can implement more enhancements to speed up query performance and make it more enterprise grade. Right, so this diagram here illustrates how does the Iceberg fit within our CDP or Cloudera data platform, and how it is the foundation for our open lakehouse. As we mentioned, that we are going to be looking at migrating our existing data on-prem and cloud and unifying them into Iceberg table format. This will become our unified data layer. While we continue to support our existing table formats like Hive external table or Hive asset, Iceberg will be our standard format that going forward in future direction. And with that, now any compute engine can insert, delete, create tables that other compute engine that understands the Iceberg format can read the same curated data within our data lake and benefit and accelerate. Thus, you eliminate all kinds of ETL across the systems, data silos, complexities, data preparation cost that businesses face today. All right, the next slide here, basically a graphic representation that we are supporting Iceberg Lakehouse across all the major cloud providers, including AWS and Azure and Google. And so this is a truly multi-cloud open Lakehouse solution powered by Cloudera CDP platform. Okay, so some of the features that we are supporting is that migration of existing Hive external table to Iceberg to help smoothly, transparently migrate and simplify our adoption and accelerate the adoption of Iceberg. We're providing simple tools, simple APIs to migrate existing Hive external tables. You can just do an alter table, setting your storage handler without having to regenerate the data or migrate the data to new Iceberg tables. All we need is build the metadata on top of existing external tables. So it's a very faster migration and time to value for our end users. We support both alter table and also Spark 3 APIs to do that. And similarly, we also support CTAS and RTAS, which is replace table as or create table as commands and interfaces to do the same migration. But this one would be reading the data from the source and then regenerating the data into the Iceberg table format. We also support table maintenance through our CDE and CML. So basically you can do snapshot management and rollback and time travel and also compaction to read the data files through these Spark APIs. All right, so let's talk about Materialized View. So Materialized View support is very key to accelerate business analytics and reporting queries in the data warehouse space. And we are implementing the phase 1, which is already done. We will support Materialized View for Iceberg table as a source, and we will also support full Materialized View rebuild. So you can rebuild the Materialized View through alter Materialized View command. And then the phase 2, which is in progress, we are expecting this to complete and merge into the upstream in the next couple of weeks, is that we will support Materialized View as a native Iceberg table. So you create a Materialized View for a source Iceberg table, the target will also be a native Iceberg table. It will be in an open Iceberg table format. And we'll also support incremental refresh of the Materialized View in the presence of inserts. The later stage, the phase 3, we will support incremental refresh of the Materialized View when the source tables have deletes and updates as well. So we're delivering them in 3 phases to basically accelerate the time to value. The customers can immediately get benefits from that, and then we can deliver these in an incremental fashion. All right, so the next thing we want to talk about is the caffeine caching. How does this really help accelerate our query performance? This is one of the key contributions from Cloudera to accelerate query performance, and specifically query compilation. This one example shows there's a TP-CDS query, that basically TP-CDS query 9, which is basically doing a query on store sales data that creates like 5 buckets, and then for each of the buckets, it is categorizing, it is doing average of sales and discount price and so on. But this query segment is particularly very interesting because for each of these bucketing of the case statements, it is reading the same files over and over again, but with different predicate clauses. So what happens is that then you are calling this plan files APIs multiple times. In this case, we are calling like 15 times. And that significantly regresses the query performance, query compilation, and impacts the query performance as well. So what we did was we implemented a manifest caching using the caffeine caching. And the caffeine caching is implemented in the Iceberg file IO layer. So it's now in the common Iceberg layer that any engine that is going through the Iceberg file IO APIs will benefit from this caffeine caching. Thus, by accelerating, you are reducing any latency issues. Every time you need to go, avoid the need to go to the object store every time you need to access the manifest file. It's a 2-tiered cache. So first we have a cache, an array of file IOs. And for each file IO, we have a content cache. And that content cache can cache all the manifest files that is read. And there is a capacity sizing limit for the content cache. It's now max to 100 MB. So as you read in the manifest file the first time through a file IO, we will cache the manifest file in its entirety in the content cache. The subsequent reads will not go to the object store, but will basically benefit from these cache cache. So you are eliminating any object store file latency issues from here, thus accelerating the query compilation. So this graph here shows that the blue line is basically external table. So if you don't have an Iceberg table when you're doing query compilation, what does the performance looks like for Hive external table? And then the red line here basically shows the Iceberg with the cache caching, and the orange line shows Iceberg cache caching with the dynamic partition pruning feature included. But you can compare, the key thing to compare is between the vanilla Iceberg without the cache caching and the red line or the orange line. If you compare them, there is an order of magnitude difference between one without the cache caching and with the cache caching. So it was able to speed up query performance in certain cases to order of magnitude performance. Note that in this case, we are also set the time to live for the cache to 1 hour. So every manifest file that you are reading will live up to maximum of 1 hour, or your maximum cache size is reached, and which then it will evict and victimize those cache objects. Okay, so now let's talk about some of the key topics about Iceberg, in particular with the V2 support. So when you have a V2 support and doing update and deletes, there are two choices. How do you generate, what form of Delta files do you do? Do you do a merge on read, or do you do a copy on write? The trade-offs, both of the options are good, but they have trade-offs. It really depends on the use cases and the rate of the data change. So let's look at the comparisons between the two. In the case of MOR, you are efficient on writes because you're only writing what rows are being changed, because you are able to track the changes at the row level. You're only capturing those row level information. The merge on read is suitable for streaming, trickle field, or low data change rate. So you're not rewriting the entire data. You're only touching probably less than 1% of the data in a file. MOR is best suited for that. But on the other hand, because you have the original data file and positional delete files, when you need to process a query, you need to read both files and reconcile the deleted rows with the existing data file to basically make sure you are producing correct rows. So that has some read amplification. And if you're doing a lot of deletes and updates in a trickle feed fashion, that could generate a lot of small positional delete files, which will lead to long tail growth. And that's where the read amplification really will show up and impacting your performance. In that case, you can actually monitor for your long tail growth or number of positional delete files. And then you can invoke a compaction to address this problem. So it solves that problem. So when is this best suited? When the percent of data change is very small, merge on read will be very, very beneficial and much more performant. Let's look at the copy on write side. The copy on write is efficient on reads, because every time you are reading, you don't have any other additional auxiliary files like positional delete files to reconcile with. So it's very efficient on reads, but on the other hand, it has a write amplification, because every change that you are doing to your file, you are rewriting the entire file. Right. On the other hand, while it is rewriting as a write amplification, it also reduces the need for compaction. Right. So it's suited for batch, bulk update, bulk deletes, where you are changing more than 50% of the data in a file or in the table. A high data change rate, copy and write would be best suited there. We are also evaluating through our internal benchmark workloads to study the performance aspects, the trade-offs, and when is one best suited for, and some of the thresholds we can understand a little bit more. We can come back with to provide our customers best practices on when to choose, what are the thresholds that to use, deciding between MOR versus copy and write. All right, so with that, we also wanted to share from our internal testing we have done so far. We have been building some targeted workloads, enhanced and augmented TPCDS workloads, incorporating some deletes and updates with varying degree of streaming inserts. Also, we took some real-world influenced, customer-influenced workloads and incorporated updates and deletes to that to stress test and understand the performance and functional capabilities. Based on the testing, we have some recommendations that we would like to share with the audience here. One, in order to increase parallelism, when you have a really large list of manifest files, you can actually address that by increasing your pool thread, the worker thread pool, by setting this Iceberg worker num threads, which is a system property that you can adjust it to tune to increase your parallelism. Thus, you can actually have much more parallelism reading and processing these manifest files. And that will actually help increase your query compilation as well. Then to reduce the read amplification. So read amplification, there are a couple of issues that we identified where, because the positional delete files through MOR, you need to reconcile them. You will have a bunch of MOR and positional delete files that are associated with a set of data files, base files. And when you're reading these and processing them, these positional delete files are repeatedly read because there is one positional delete files that maps to multiple data files for the rows that are impacted. And so for each data file, you are reading these positional delete files multiple times over and over again. Thus, it is impacting our read amplification, also the query performance. And also we identified some inefficiency in the way that bin packing is done today in Iceberg. So address that. You can monitor for the long tail of the positional delete files or delta files growth, and then you can compact them to address that. The last couple of things are to speed up the drop table. So when you have a really large table and you're doing the drop table, by default, it will drop the metadata, it will also drop the data. And it's basically going out to the object store to drop all the data files, which is going to be quite time-taking, time-consuming. And if you wanted to avoid that and you wanted to simply purge it and not remove the data files and later take care of the data files through your maintenance operation, you can set these two properties, which is external table purge equal false, and then the garbage collection enable equal false. What it would do is that it will basically remove and delete the table metadata in your catalog, but it will not touch the data files. So that way your drop table is much more faster. The last one, best practice we would like to recommend as a tuning option is, if you want to increase concurrency, when you have a concurrent reads and writes going on, and they're going to be doing a lot of updates and deletes. So each change to the Iceberg table needs to produce a new snapshot and needs to update the metadata in the catalog. So there will be a lot of contentions going on because they're all contending on the table's metadata pointer swap. So you can actually adjust these two parameters like commit retry, main weight, and commit number of retries, right? And that will actually help you increase your concurrency as well as reduce any commit failures due to write-write conflict that will be happening. So those are the best practices that we would like to recommend. All right, now let's jump to the use cases. So based on discussions and close engagement with our customers, our enterprise customers, we basically gathered these are the top use cases that our customers would like to adopt and accelerate on Iceberg. So as I mentioned in the earlier part of this session, today's problem is that there are endless number of silos that are happening in our customer deployments, and each business unit may have their own software vendors, software solutions, software stack that complicates and makes it much more challenging for them. So customers basically say, we want one platform, we want to consolidate and unify, eliminate all these silos so we can really spend our valuable time on getting business insights and not dealing with these complex challenges of data preparation, cleansing, moving, and data management. And this will actually simplify their entire architecture in their enterprise. So that's one big use case where we will see Iceberg can really help them solve this problem. The other one is that increased visibility and risk and security management. So they would like to see like who had access to what, and using the time travel capabilities that Iceberg provides, they will now be able to have much better insights into and have a control on the access and authorization and data management. So let's look at a couple of the customers that we are talking about. One is a global auto manufacturer. So the challenge today is that they want to have a predictive maintenance, so they can actually know when particular machine, the cars and their systems needs maintenance. So they can actually engage with the customers proactively, provide them notifications on maintenance and service, and also improve their overall customer satisfaction. So they have their systems, but they don't want it to actually have much more performant and accelerate solution. And today, and that's why they wanted to move to Iceberg. With Iceberg's partition evolution, which they can actually handle the scale of the data growth and in-place partition evolution. And with partition pruning and filtering capabilities that Iceberg brings in, now they're able to do much more faster query processing. This actually resulted in 10x performance in their early POC runs. So where they really got benefit is that by eliminating unnecessary data scans, by doing the data skipping and only scanning the data that the query is interested in, by exploiting all this partitioning, pruning, and min-max filters, and all the capabilities that Iceberg is providing, they are able to see 10x performance speed upon that. The next customer is a global pharmaceutical company, and this is the one they wanted to have much more control on their security, governance, and authorization, and InfoSec. So they have a Ranger, they have all their Ranger data coming in. They would like to understand who had access to a particular data set and data assets, when and why, and so they can have a much more control on and insights on the data governance. So using the time travel capability, they are able to take advantage of Iceberg to meet their business needs here. And flexible partitioning, their data ingest is basically based on Atlas timestamp, and when the data comes in through, but the query is based on user ID. They want to query on which user had access to which particular data set and what point of time. Right? So that basically gives us much more control and ability to understand how the data is being accessed and used and who had access to when. So this is how Iceberg is solving some of the customer challenges today that we have interacted with, and we are actually helping very closely, working with the customers to deploy and understand some of the performance aspects from their POC, and they will eventually be migrating to Iceberg. With that, that concludes my session. So if you have any questions, we'll be happy to answer now. And then I will pass it on to Shaun, who will talk about our reference customer, TerraNet, who is also migrating to Iceberg, and talk about their business use cases and value proposition they are getting from Iceberg. Thank you, everyone.
Any questions? Any questions? No? All right. Oh, pizza. Pizza's here. All right. So I'm here, Shaun Ahmadian, product management at Cloudera. Obviously, everyone who's also online, really appreciate you guys attending. I think in last count, I think I see about 80 people live streaming it. So really great turnout. So as a product manager here at Cloudera, I work a lot collaborating with our data engineering counterparts at our customers. And a lot of the stuff that Vince was talking about, the scale and performance that we really, with how much zettabyte of data that we have, it's a lot of data, then we see the problems. But if you guys actually, many of you out there are data engineers, you probably could understand what I might be referring to, paradise. Data engineering obviously has a lot of complexities to it. Obviously, that's what we would love. We would like to get blue skies, everything works. You never write a data pipeline, and it will always have issues, especially if you're working in a setting where it's like large scale, you have counterparts. It's not just yourself, right? If I just go and I create a pipeline on my own, that's really not at scale. But the moment you have to meet SLAs, there's a lot of issues. So bringing a little bit of the theme is that there's a lot of stuff below the waterline with when you're dealing with data engineering pipelines at scale. And I like to refer to them as data management mines. And again, I assume many of the folks out here, data practitioners and data engineers, you kind of start understanding that there are a lot of challenges when you're doing data engineering. And that's kind of what I'm referring to data management mines, not just like creating your application, but actually dealing with the data and the infrastructure behind it. And obviously that was a lot of the reasons why companies like Netflix obviously implemented initially Iceberg was for this. But let me kind of talk to you about one use case that kind of highlights it, because Vince was talking to a lot of the other customers we're working with, but TerraNet is kind of a good example. So their typical pipeline is CDC, change data capture. You might say, Shaun, that's pretty straightforward. We do it all the time. I'm like, yeah, that's true. But to do it at scale, and as you really think about it, it's actually pretty complicated as you get deeper into the analysis. So we have TerraNet. They have their data engineering team there. They're kind of curating the data. And what is kind of their typical workflow, right? So you ingest some data, you identify the deltas, you apply those updates, assuming those changes. You take backups potentially. There's reasons why you would want to do that. And then usually for compliance and auditing purposes, you usually do some level of backups. And then again, if you're meeting other customers, typically you'll have a central data team or central data engineering team, and they're responsible to providing the data to other consumers of it. And so what ends up happening is they have SLAs that you have to meet with them, and if there are issues, you're going to have to revert, identify what's going on. So usually this is kind of a common pipeline. It's not that different what you would typically do, but in this particular case, this is kind of the steps that was being done for this change data capture use case at TerraNet. Now, as you kind of dig into it, and as TerraNet experienced, or as they were implementing this over the last few years, they kind of realized those data management minds that were there. So let's kind of dig into them. So you start kind of articulate what those are. So very, very kind of at a high level, like the very beginning, you actually have to think about refresh frequencies and number of sources. So at Teradata, they actually had thousands of tables and hundreds of databases that they're mapping out, and they actually had to refresh on a frequent basis. Now, many large customers, as you can imagine, they're doing this on a daily basis. That's pretty agile for them. But you can imagine what are the next steps that the business really wants? It's more agility. They want more frequent refreshes. So as you really think about it, as you look at your data pipeline and the infrastructure and the data management layer, you have to ask yourself, am I scalable? Can I handle refreshing this data on an hourly basis? What if I want to do it every 15 minutes? Can you handle increasing the sources of your data from 1,000 tables that they have today to 2,000, 3,000? So really at the top of mind, it's like the frequency of these refreshes, increasing those, and the number of sources increasing potentially over time. Can your data infrastructure, can your data management layer handle this? I know your application layer probably can do it, but can your data management layer handle it? Let's go further down the pipeline. This is the little pop quiz. I think Vince actually kind of alluded to this. There are tunable update strategies. Like you have to think about it and say, am I a heavy read or am I heavy write workloads? How about your upstream? How about your downstreams? There are implications on how you think about update strategies of your data. So again, think of the data management layer. Are you thinking, is your data management layer actually able to give you those knobs to handle this in a tunable fashion? How about a little bit further down the line? So TerraNet, they have for compliance and auditing reasons, they actually have to maintain backups. When they do perform updates, these updates go back anywhere from retroactively 30 to 60 days. So they're updating potentially 30 or 60 days out, obviously in the future or historically, once the day comes, that they could be going back that far. And so they have to start maintaining these backups. Now, what happens when you have, instead of 1,000 source tables, 2,000 source tables? How are your backups being handled? Think of purge policies. Okay, I have all these backups. How do I manage them? Is there an infrastructure? Is my management layer actually supplying that capability? And this is kind of my favorite, is at the end of the day, your pipelines, they offer something, and it's not just to you, it's to other people, which is in your business. And they will come back and they will notice, and this is what happened in TerraNet, they'll say, I've noticed some issues. I don't think this update was correct. Because again, things are going back retroactively. They'll analyze it maybe a day later and say something's wrong. So you actually have to be, in a very efficient manner, go back to your business counterparts, your partners, and say, yeah, okay, we saw the issue. I can revert this very quickly for you. So at least you can go back to the previous state of the data. And then we will resolve whether application logic issues we had or if there's an incorrect update. Again, do you have the management layer to actually do this? And Terranet had to implement all this by themselves. Okay, so imagine across all of this, all these data management minds is something that Terranet had to actually address. So this is obviously where the power of Apache Iceberg comes in, and this is why they were really interested in attacking all these different problem vectors within this example use case of their CDC. And so if you kind of go along and you can start seeing how the features of Iceberg actually handle that fairly well. Obviously, various aspects of petabyte scale, you really don't feel too bad about the number of tables and your data size is increasing. Configurable updates, we were talking about copy on writes and merge on reads. This is actually a key aspect of what Teradata was actually evaluating. We had copy on write, that's kind of has been there, but merge on read is fairly new. It's actually something that they're trying out as we speak, because then they wanted to understand for their workloads, how do these things compare? And Iceberg gives them those tunable parameters to think about their update strategy. Obviously, compaction goes without saying. Imagine how you handle and maintain efficiency of your pipeline at the data management layer, automatically handled by Iceberg. Snapshots, again, goes without saying, something that Iceberg is actually giving them. Instead of them having to manually create or come up with the system to do that, there's an expiration, basically a purge policy that Iceberg can give you, which is fantastic. And then, of course, when their business partners come and say there were some issues, there is time travel, point-in-time queries that can go back, revert to older snapshots, keep going within their business process within a matter of minutes. I mean, literally, this is kind of the efficiency gains that Terranet was looking for. And that's why it's really important to think of Iceberg, of everything that you saw, is really, really reducing those data management complexities. And hence why sometimes I feel like we're doing this as a data engineer, which is we're demining our data engineering pipelines. So this is kind of all I had. This is my quick spiel about our use case at Terranet. And I think now it's time for QA.
Yes.
Yeah, so if you have any QA, any questions?
So we are doing a mini QA right now. If you guys have any questions for the slide presentation done by Vincent and Shaun, any questions?
So the one question, can you want to repeat the question?
Yeah, so there's a online question. I think one of the folks asking is that why Cloudera actually adopted Iceberg in the CDP platform. So we actually compared all the open table format out there. And what we believe is the Iceberg is the best in terms of open source community support, as well as a growing set of compute engines. So this is one of the reasons that, and also some of the unique features that actually one of the unique feature will be demonstrated in my live demo. So we're gonna show that to you. So there are some unique features that we're seeing compared to other table formats out there. So this is why we actually adopted Iceberg as our table format for our CDP platform. Yes?
So I had a question on merge on read versus copy on write. Merge on read performance should be basically a function of the backend storage's performance in terms of number of concurrent reads it can perform. So the trade-off between merge on read and copy on write is really about the capability of the backend versus what the application needs.
So I'm gonna ask Vincent to answer. Vincent, can you repeat the questions so that folks online can also? There's no mic.
Yeah, there's no mic. Yeah.
Sorry, can you repeat the question again?
So merge on read versus copy on write is the trade-off.
Yeah.
It seems that merge on read, the inefficiencies come from what the backend can do in terms of number of concurrent reads versus copy on write, which is a fewer RPC calls to the backend. So is it like if you have backend sufficiently powerful, you would never choose copy on write, you always go with merge on read?
So when you mean backend, are you talking about the compute engine or the storage? Storage. So not necessarily, because it really depends on how big.
Can you repeat the question? Okay.
So the question was the trade-off between merge on read and copy on write. Isn't that a function of how efficient the backend is? And in this case, backend, he was referring to the storage layer, right? Am I right? Right. So not necessarily. So it really depends on how large number of the delete rows are that you need to really reconcile with, right? So you got to basically do either the two ways to do it. You can basically generate a bitmap, just kind of what Iceberg does. And then you got to basically look at what rows are deleted from a base file I need to exclude so I can produce correct results, right? So the larger the number of rows that you have, you're going to be spending time in lookup and hashing and finding which rows are deleted or not. The other way that some of the engines are doing it, they're doing anti-join. So either way, either you do a bitmap lookup or you build a hash table to the anti-join, you are spending time. And that is where most of the time is also spent. And now, with respect to, this will actually add up because, as I mentioned, in a read amplification, one delete file can be associated with multiple base files, base data files. Then you are now incurring repeated reads of the data files because you don't have a very good clustering, very good bin packing, then it will further amplify that. So to address that backend storage thing, you can cache them. You can have to cache those files into your SSD, but still it will not address the performance bottleneck to reconcile those deleted rows. So you got to really implement a more novel, innovative solutions to optimize it. And we are currently working on in Impala an optimized solution to speed up this anti-join processing for that to further accelerate our query processing, especially to handle large deleted rows. Does that answer your question?
Yeah.
Okay, thank you.
So what we're gonna do is open up for other Q&As. So this is just a mini Q&A. So right now, what we're gonna do is actually do a live demo. A couple of things that Vincent highlighted, as well as some of the unique features that we're seeing offered by Iceberg table format. So let me just coming over here. I don't know if you guys haven't seen this, our Cloudera data platform. So what I usually do is just coming over here to Cloudera data warehouse. Let me see. I have two pre-warmed up Hive virtual warehouse. So this is a Hive virtual warehouse already, and there's another one that is Impala virtual warehouse or startup already. And I also have a two browser open, one for the Hive editor, one for the Impala editor, right? So want to make sure that's a Hive virtual warehouse. So a couple of things that what I want to show here is, let me just go to my slides here, go to stream mode. So I'm going to demonstrate four things. In-place table migration, right? So we have a lot of Hive customers on Hive external table. So what the easiest, the best way for them to migrate from Hive external table into Iceberg table. So I want to show some outer table comments and then using that to migrate into Iceberg table. Vincent actually showed that earlier. And also a very unique feature within Iceberg is called the in-place partition involution, right? So normally when you do partition involution, guess what? You have to regenerate entire table. If you do that with 1 petabyte or petabyte size table, it's going to take a long time to do that. But with Iceberg, we have the capability of in-place partition involution. So I'm going to demonstrate this capability as well. Then, of course, all our data warehouse customers asking for time travel capability. So I'm going to do that as well. You can do time travel based on the snapshot ID as well as timestamp. And also, one last thing that also very unique to what Cloudera solution we offered is we're also going to do the fine-grained access control, right? What is fine-grained access control is the row-level filtering, column masking. So I'm going to do that, demonstrate that. So let me actually switch to the browser here. So very simply, this is my Hive virtual warehouse. So I already kind of paste. I'm not going to type in the comments, but so let me do the first. Let me do the migrating table. I have an existing Hive external table. I want to migrate those existing Hive external table into Iceberg, and this is simple alter table commands. And all you need to do is actually set the table property, right? So that's Hive Iceberg storage handler. So let me just do that. All right. the results is successful. So now the table is being converted from external Hive external table. Let me just go there to show describe format. So I want to show some table property here, and what are table property? First thing that you will notice that this is a migrate in terms of a migrate to Iceberg. So you know that this table is actually being migrated from external table. And then what is the table type, right? So this row is important. That is Iceberg table format. And other things that you're going to see, SERDI library. So this is Hive Iceberg SERDI input output format is also Hive Iceberg input output format. And also, yeah, here's the location is in the AWS S3 bucket, right? So now we know that we have a table that being converted into Iceberg table. Now, the second things that I want to show you is the, let me see. So that's the in-place partition evolution. So let me go there. So I have, so this is my create table statement here. Oops, sorry. Hopefully you can see that now this is partition by year, right? Think about if based on your table ingestion pattern, you want to actually change the year, let's say into year to month, right? So this is something that if your original table is partitioned by year, then this is in terms of in-place partition, you want to actually partition into year and a month, right? So I'm not going to run this create external table because the table is already there, but I just want to share with you is that the original table is partitioned by year. And so, and then I also already load data, the data sets that I load, that's the airline data sets. And then now it's up into 2006, right? And one other thing that what I like to do is actually, that's the in-place partition evolution. Very simply, alter table commands, right? Set the partition spec year to month. Let me run that. All right, success. So let me show create table. What I want to show here is now the original table was partitioned by year, and now I changed the partition spec to year and month. So let me run show create table. So now partition is actually by year and month. Now, why do I want to do that? So let me go to Hue editor. So I have Impala queries written here. So one of the things that what I like to show here is in terms of partition evolution, let me go here. So I want to show run query plan on this one. And one of the reasons that, of course, one of the reasons that you want to do that is actually, reduce the data sets you're going to scan. So let me run this. Oh, actually, no. Before running, just show the explain queries, right? So this is the year 2006. Now, year 2006, and I want the month 12, December. So what I want to share with you is that what kind of data sets that you are scanning. I'm scanning 140 megabytes, okay? So that's before the partition evolution. So now, after 2006, 2007 is when I changed my partition into year and month. So let me do a show plan for this one. So the data set's supposed to be much reduced. Do explain query. Now, as you can see, the size become 11 megabytes, right? So it's 10 times less. Why do I want to do that? Less data you scan, higher the performance, right? So simply put. So this is what we're talking about in place. The really some of the benefits you're going to see. One is you don't have to regenerate your data sets. The other one is really reduce the data sets you need to scan in order to improve the performance, right? The next thing that I want to share with you is the time travel. So let me go to my Impala editor. So what is the time travel? Now, remember, my original data sets is up until 2006. And then after that, I changed my partition schema into year and month, and then I insert more data 2007. So what I want to do is actually take a look at my data sets history. So describe history. All right. So I actually updated, so this is my original data sets, and I have 3 different snapshots, right? So what I like to do here is do time travel. Actually, let me show this one, snapshot ID, control copy. So this one will actually give me up until 2007. Let me do time travel by snapshot ID. So time travel, you can specify either snapshot ID or timestamp. So let me go here. This is the snapshot ID. And this will give me the data sets up until 2007, right? So now if I do the scrub history again, I want to actually go back to 2006. So let me get the snapshot ID for that one. Okay. Let me go back to, that should be 2006. And then this is my snapshot. All right, my data sets now goes back to 2006, right? So this is a time travel feature that we talk about. The last thing that I want to share with you is really the fine-grained access control. It's very important. And so one of the things that we're seeing in the airline data sets that we have, while each plane have a tail number. And the tail number is actually pretty sensitive, right? You can track all the fly where it goes and where it's coming from. And so what we want to do is actually we want to column masking for that the tail number for the plane. So let me, and then so how we're doing this is since we have a Ranger integration. So in the Ranger user interface, we defined a Ranger policy. Right. So in that Ranger policy, you say that we want to actually column masking for the tail number. So so I'm not going to show that user interface there, but this is I just want to run the query for the sake of time. And what you're going to see is that all the tail number here is actually being masked. Essentially, it's hashed. Right. So this is why you're not going to see it because it's sensitive information. It's masked data. So this is my simple demo in terms of what we did, some of the things that Vincent highlighted in his presentation, and some of the unique features that are in place, partition evolution, right, time travel, and also some of the fine-grained access control. And with that, I'm going to turn the floor to Win-Yu, and he is going to actually share with you some of the interoperability between Hive, Impala, as well as Spark. And so this is one of the promise of the Iceberg table so that you can do the compute engine interoperability. So let me give you the, it's okay.
Hello, everyone. My name is Wing-Yu Poon, and I'm a software engineer in the Spark team at Cloudera. Currently, I work on the Spark support for Iceberg, along with a couple of other folks in the Spark team. In the Cloudera data platform, Spark is available in several different form factors. So there is CDE, Cloudera Data Engineering, which I think Vincent mentioned before, and Shaun also mentioned. So that's one of the managed data services along with CDW. So in CDE, you can schedule Spark jobs, pipelines of Spark jobs, and these run on Spark on Kubernetes. There is also a more traditional form factor. So we have in CDP public cloud, we have Data Hub clusters. So these are the what people might be more familiar with from earlier the CDH stack. So you have a VM cluster, in this case in the cloud, AWS, and these contain your usual, services. So here we run Spark on Yarn. You can also run Hive and Impala and various other components in these Data Hub clusters as well. So in CDE, of course, we have support for Iceberg with Spark for several releases already. In Data Hub, we have an upcoming release, which is 7.2.16, which is going to be GA quite soon. And this is the first release where where we will have Iceberg support in Data Hub. So you will be able to use Spark and Hive and Impala all with Iceberg in CDP 7.2.16. So here I just going to show you. Here I have two Data Hub clusters. One is set up with Apache Spark 3, and the other is set up with Impala. They're both 7.2.16 clusters. And here we have a Spark 3, and in another one we have Impala. And so here we're gonna, I have a couple of terminals open here. I'm gonna run a Spark 3 shell. And in another terminal, I am running a Beeline. The Iceberg that we're shipping in 7.2.16 is Iceberg 0.14.1. Now, of course, you probably know that we recently have Iceberg 1.1 release, following soon on 1.0. 1.0 and 0.14.1 are very close. They're really, for functional purposes, they are really the same. It's just that in 1.0, we set up what is the API that will be supported. So anyway, the thing I want to point out here is that here, in order to use Spark with Iceberg, you can just run Spark 3 shell, or you can run Spark 3 Summit. There are no additional configurations needed. We have already set up the Iceberg Spark runtime join, the class path. We have configured the default Spark catalog to be the Iceberg Spark session catalog. So you will understand both Iceberg and non-Iceberg tables. And we have set up the Spark SQL extensions to include the Iceberg SQL extensions. So all the full functionality of the Spark SQL support for Iceberg is all available out of the box. So that's the thing I do want to point out. So the first thing I want to show you is creating an Iceberg table. And one of the ways you can create an Iceberg table is you can create it from a data frame. So the first thing I'm going to do is I'm going to load up a data frame. So I'm just loading a CSV file into a Spark data frame. This is a CSV file with 500,000 rows plus the header. So with the header, you can infer the schema. And basically, this represents like a customer table. Here you can see the schema. There's some various information about the customer. And so what we're going to do is we're going to use this basically data frame v2 API to write this out to a table. Okay. So the syntax is basically you do write to and then the name of your table. Here the database is Spark Iceberg, and I'm naming a table customer, and you need the using Iceberg so that you are creating an Iceberg table. You do a create, and this does the creating the table. And so let's take a few seconds. Once the table is created, I'm going to go over here in Beeline, and I'm just going to run a show create table on this customer table. And then you can see so I'm running the show create table. And here you can see that the table type is Iceberg, and it's stored by the Hive Iceberg storage handler. So that's how Hive recognizes that this is an Iceberg table. This is the Hive Iceberg storage handler. So that's how Hive knows what kind of table it is. Oh, sorry, didn't mean to pause that. So then, here is another way you can create an Iceberg table. So here I'm going to do a create table as select. The first table I created is an unpartitioned table. This one is a partitioned Iceberg table that I am partitioning by basically in Iceberg you have these partition transforms. So truncate is one of the Iceberg partition transforms. So this table is partitioned by truncate customer last name 1. So basically we're partitioning by the first letter of the customer's last names. Okay, so having done that, we have a second Iceberg table called customer partition. So one of the interesting things about Iceberg is that you can query the Iceberg metadata through these pseudo tables called metadata tables. So the first one I'm going to show you is this metadata table called partitions. So here what I'm doing is I'm doing a select from this the partitions metadata of this customer partition table. And you can see that, well, you have these 27 partitions. What this partitions metadata table tells you is, okay, these are the partitions, and these are the record counts for each partition. And then these are the file counts. So in this pretty small table, like each partition basically just has one data file. And they have different amounts of records in them. And you can see that the partition X is the smallest one with 53 records. So I'm just going to do a select from this particular partition. So the select is where C last name like X%. Okay, so basically all the customers' last names starting with X. So then you would just select things from this partition. Okay. And then I'm just going to show you that you can run this in Hive as well. And it has returns the same results. Here I'm just showing you the last name, first name, last name, and the email address. And we can also query this in the Impala cluster. Here we have the same 53 records. Okay. Okay. So one of the things that here what I want to show you is the Spark UI. So in the Spark UI, you can go to the SQL tab and you can click on query, and then you can see the graph for that query. Here is actually an improvement that's made by one of my colleagues, Sumit Gajar, in the Spark team. So he made some changes to upstream Spark. So basically, Iceberg is implemented as a Spark data source v2. So when you do a scan of a data source v2, in this Spark UI, normally all you can see in this node here, you will just see the label as batch scan. So that's not very informative. You don't know what is scanning. So Sumit made some changes, and now it shows, okay, this is actually an Iceberg data source v2, and this is the table, the database, and the table that we are scanning. So this is something that small UI usability improvement that we made. And here you can see that the scan is 53 rows, and after the filter is still the 53 rows. Here I'm going to run the query on the first table, the same query, but not of the partition table, but just of the customer table. This will take a little longer. And of course, it's still the same results. And we're going to look at the Spark UI and see what it looks like for that query of the unpartitioned table. And here you see that this is for the customer table. And you can see that here actually in the scan, we are scanning files with 500,000 rows. So one of the things is we don't see the number of files which are scanned. So this is actually another improvement that I made. In Spark, there are this thing called custom metrics. So I've added some custom metrics to Iceberg. One of them is the number of file splits which are read in a scan. And the other is the number of deletes which are applied they're applied in a scan when you're reading a V2 table that has delete files applicable to those data files. So that's actually in the recently released Iceberg 1.1. So obviously it's not available here because we have 0.41. But then you'll be able to see the number of file splits that are read. But this doesn't mean, okay, so what this means is that we're reading some files and the number of rows in the file is 500,000. Then after that, the filter, you have like 53 rows in this part here. And of course, that's what you have in your output. Okay, so the next thing I'm going to do is I'm going to upgrade this table to format version 2. And so the way you do that is basically you do an alter table and set the format version table property to 2. And then this will give you a V2 table. So one of the things about the V2 table is that there are these things called write modes. So there's like a write delete mode, a write update mode, and a write merge mode. And the default values for these modes is copy and write. So by default, when you upgrade a table to V2, it doesn't mean that you are using delete files. You're still going to be doing copy and write, same with V1 by default. But our expectation is that when our users want to upgrade their table to V2, they want to use delete files. So they want to use merge on read. So we made some changes to our downstream Iceberg so that when you either create a V2 table or you upgrade a V1 table to V2, we by default we set all these write modes to merge on read for you. You can of course explicitly set them yourself to whatever you want. But if you don't do anything up in our Iceberg, you get merge on read. So that's something I want to point out. And so the first thing I want to do then is to run an update. So in this table, you can see, okay, I have these 53 users in this partition. There's this Mildred Shaun with this particular email address, and I'm just going to update this user record to update that email address. So we're going to set a new email address. And so I'm running this update here. And after that, I'm just going to query the same partition in Hive. And you should see now that, oh, see Mildred Shaun's email address is updated. And similarly in Impala, the update will be reflected right there. Okay, so the next thing I'm going to show you is, I'm going to show you another metadata table. So this metadata table is called files. The one I showed you before, partitions, actually is sort of an aggregate view on files. Anyway, so this files metadata table has actually a lot of columns. I'm just going to show you a few columns from it. So the content, partition, and record count from this guy. So what content means is that, okay, so what we are querying is what are the files for this partition. So you see in this metadata query, the where clause is where the partition is equal to this struct. Basically basically this so in this result, what we are seeing is that content 0 means it's a data file, and content 1 means it's a delete file. Actually, it's a positional delete file. Content 2 would be an equality delete file. We don't have any equality deletes yet. So what this shows is that we have basically a data file with 53 records. Then we wrote a delete file with 1 record to delete that Mildred Shaun record. And then we wrote a new data file, again, and content 0 with 1 record, which is the new value. So that's how that update was implemented. Okay. Oh, actually, in the interest of time, I was told that I should. I'm going to skip a whole bunch of stuff. Because why is this not? So I was going to show you merge into as well, okay, I'll just show you merge into real quick. So basically, here I'm running a merge where I'm taking the source from the original unpartitioned table customer, and I'm basically updating the customer partition table, and whatever was not in this customer partition, because I already deleted it, I would insert it. So, then the result of that is what you see in that last metadata table query up there, where basically you have 2 deletes. There's the 1 and 1. First, I deleted 1 file and then 1 record, and then I deleted 3 records because then I ran a delete I didn't show you, and then I did an insert, which is the 3 records that I inserted back. Okay, so I was going to show you this time travel also, but Bill has already showed you the time travel, so that's not so interesting. So I'm going to try to fast forward that. Okay, so I'm going to fast forward that to compaction. So one of the things you can do is from Spark is we have these procedures that you can run, and one of the procedures is called rewrite data files. So because we have this small partition and we have written like these delete files, so what we want to do is to basically consolidate all these updates that we've done and rewrite everything into like a new data file. And compaction will allow you to do that. So I call this rewrite data file to do that. But after running this rewrite data file on this partition, so with the procedure, you give it the name of the table, and you can give it some filters. So in this case, the filter is that where last name is starts with X. But what we get back is that the rewritten data file count is 0. That means nothing got rewritten. So the compaction didn't actually happen. So why is that? So the reason for that is because there are actually just 3 data files in this partition. So the minimum, there's like a minimum file count that kicks in before like the file group would actually get rewritten, and the minimum is 5 default. So it doesn't meet the criterion, so the compaction is a no. So what we can do is that we can change it. So we can set min input files, and we can set it to 2, for example. But another way to make it happen is we can use this delete file threshold. So what the delete file threshold means is that if there's even like a data file with any delete file applicable to it, it's going to qualify for a rewrite. So then in this case, we have some delete files, so it got rewritten. And here, this is the rewriting 3 files. This is the stage where it happened. And what I'm going to do here is I'm going to show you can query metadata table with time travel as well. So this is maybe a little something people don't know about. So what I'm going to do is I'm going to query partitions with not the current snapshot, but the one right before that, before we ran the compaction. So I'm going to paste in the snapshot ID here, and we're going to query this partitions metadata again. And what you see here is that in the partition X, you'll see that there are 3, the file count is 3. So there were 3 data files before, and it says the record count is 57, because that just means it's the sum of just the record counts for each of those data files, okay? But then now I run it again, and you can see that the file count is now 1 at the end. So that shows like the compaction, how it happened, and you can see this like through querying metadata as well. And that's it for my demo. Thank you very much. Yeah, thank you.
So the next speaker is Sam from Netflix. Thank you.
All right, how's it going, everyone? So first, thanks to Cloudera for putting this together and for being such great hosts. My name is Sam Redeye. I'll be talking a bit about the REST catalog, but I think a little bit of a different talk than what some of the REST catalog talks have been all year. It's a little bit about me. I'm a software engineer at Netflix. Some of my contact and email and stuff is up here. Feel free to reach out for anything. So just high level, I just have one slide on like what the REST catalog actually is for Iceberg, for anyone who's not familiar. So REST interface for doing catalog operations. It's an abstraction over all the different catalog implementations that exist out there. So Hive catalog, Glue catalog, they all can sort of be, you can add the REST catalog as a shim over top of it. It allows access to Iceberg metadata from any language, because simply anything that can make a REST call can, execute any of these catalog operations. And so some of these benefits are like resolving multiple client versions. There's a good dependency story around it. It makes integrating Iceberg easier. But this talk, I kind of don't want to talk about the main reasons why the REST catalog is a good option to use. And I want to talk more about some of the different use cases I think that go outside of simply data processing and what we think about when we think of Iceberg catalogs. So I'm going to touch on a couple of different scenarios, and I'm going to go through them. Some of these are real, some of these are more potential ones that could possibly benefit out there. So one thing to consider in this one scenario is the fact that compute engines are not the only consumers of information about a data warehouse. So there's a bit of a flag there, but so traditionally when we think of a catalog, we think, okay, you can have different compute engines, right? Spark, Trino, Flink, you have your data warehouse, and Iceberg provides metadata over all of these to read various files on data warehouses. But there are all these other applications out there that are not compute engines, right? And their purpose is not necessarily to understand the representation of a table in terms of data files and run computations on them and make commits, right? So some of the questions that these tables have are like, what are all, it might be a bit small to see on there, but I put like, what are all the table names in the database, right? Does this column actually exist in a table, right? Or another example here is, when was the last time the table had a commit, right? Or how many records are in this table? So all these are kind of questions around, are we in the matrix? Probably can't answer that from a REST catalog operation, but the idea here is that these are not about actually reading data, and they're actually not about making commits to the table. They're general information that applications may want to know about what happens in, or properties about your data warehouse. So one use case that's actually in existence today, some people write unit tests on their Spark ETLs. It's not the most common thing in the world, but a very high level one that people always want to do is, can I write unit tests that run very quickly and catch funny schema errors or syntax errors in their SQL? So if you don't care about that, what you do is you have your source code for your Spark application, source control. You ship it, and then you get an exception that some input column doesn't exist in the table. And you actually deploy it. Maybe you have a sandbox environment, so it's okay. I deployed a sandbox environment, and I got an error. Now, if you're clever, you say, oh, I have CI/CD, I have Jenkins, and so I actually run a script. I go into my development environment because no one's going to let you query run your compute engine as part of a CI/CD pipeline. So you say, I'll go get some sample records from my real table, and I'll copy it in, source control it with my code, and that way, when I ship to Jenkins, I can actually run a local Spark session. I have some sample record. I can load into a data frame. I can run my application, and I can do some unit testing there. So that works, right? So you say, okay, well, I'm good. That's set. It works. So you do a couple more deployments, and then all of a sudden, the table doesn't even exist, right? The table was dropped, and the big issue here is that every time there are changes that happen in the warehouse, you need to actually regenerate these samples, and it's this weird mechanism that you do for unit testing your pipeline. So the important thing here is that the actual data doesn't matter, right? So if Iceberg is just accessible through a REST catalog, you can make a REST call. You can actually generate a random schema. You can generate random data that matches the current schema of the table. So a simple REST catalog call, you can actually get one, confirm that the table exists, two, get the columns and the column types. You can generate random data as part of your CI pipeline. You run a local Spark session, and you can actually confirm that this would all work. So this currently is part of a tool at Netflix called Dataflow, where you can specify your input tables, and you can actually run your unit tests in a local Spark session as part of CI/CD. So that's one example of a potential use case. The second one I think is pretty obvious, that you can build a web UI, and I don't have points to make here, except if you just look at the Open API spec for the Iceberg REST catalog. By the way, where I create this, if you go into the Iceberg repo, you can just take the Open API spec there, the JSON file, and drop into the Swagger editor, and then you'll see these different routes. But you see, you can list tables, you can list databases, you can you can check if table exists. So these are a lot of different routes that you could create a user experience, a web user experience using any of these. So that's another potential use case. And here's one that's, I call them, I don't know if this is an official term or if anyone else uses this, but I call them like data warehouse adjacent applications. And these are all these different kind of applications that produce queries. They don't actually run queries, but they produce these queries. So they're defined somewhere else. So just one example is the data virtualization spaces. There are different tools that do this. But the idea is you specify, disappeared. Okay, here it is. So you specify some source tables in the system, and you specify some transformation on those. And then you can specify some subsequent transformations, and then what these, I don't know why he's disappearing and coming back, but that's right. And then essentially when someone selects these named nodes, you get the actual query representation. And there are a lot of things that do this, to do like different dimension discovery, and there's a few things out there. But a big part of this is the same problems of, you create this data virtualization system and you don't know, has this table been dropped? These are questions that this other system may want to know. Does this table still exist? It's defined here. Do these columns exist? Are the types valid? Because there's a lot of type inference that happens here. These are, these tables could be materialized, but they don't necessarily have to be. You need to know the column types to infer, can you actually sum this? Is a sum aggregation possible on this column type? And let's go through one more time. The idea here is that the REST catalog could provide these validations. So you can check all the myriad of things that you can do as simply a catalog operation, you can do with the REST catalog. And then, by the way, from battle time, just jump up and down, wave your hands. And here's one that I added in. This is probably more of the, we'll see where this goes, but you could technically have multiple catalog implementations underneath the REST catalog entry point. So if you wanted to have namespace mapping to different catalog implementations beneath, you could completely do that and have the REST catalog entry be a single catalog entry point. And it's possible, but there are some joins across different underlying catalogs become different, so you'd have to have certain guardrails implemented at the REST catalog server layer on your backend, but it's ideally possible. And I think the bigger point to make here is that if you're using the REST catalog and you have that contract with Iceberg clients, you get a lot of benefits, like dependency on the client become easier, but a big one is that you can do a lot of things behind the scenes on the server, on authorization is a big one. That's part of the open API spec. But it gives you a lot of control server side to add certain clever features. Is how I put it. So another one here is write audit publish pattern. So this is a common one. Yeah, I've done a few talks about it, but it's an integrated audit, sort of a feature that's part of open source Iceberg. And there are a lot of audits, if you look at just a subset of these, that don't actually require you to run a Spark query to figure out. There are things that you can figure out from Iceberg table metadata. And the common patterns today actually run queries to figure these things out. With REST catalog calls, you can make these very, very fast. So if you think of, backfills, for example, where you're doing you have a bunch of distributed processes and you're running additional query for a daily backfill over 2 years, even though it may only take 2 minutes to check if your primary key column has nulls, those are 2 minutes for every day, and that adds up. If simply you can do a REST call, look at the null count in the Iceberg metadata, you could actually there'll be a significant increase in the performance of the audits. So if you think across an organization with hundreds of thousands of ETL processes that are happening, these seemingly small performance improvements from a 1 minute query to just making a simple REST call has a tremendous amount of value collectively. And mainly because audits against metadata is cheap if it's just an API call. So that's all. Just some more information here. For everyone here, I think looking at the blogs and talks section of the Iceberg site is really good. There's new ones on there. Sometimes we miss some, but it's simple PR to add any. So it's a good place to go. And the community, of course, join the community.
5 minutes, mini Q&A. You guys have any
Questions?
Okay, thanks for the talk. So does the REST catalog maintain any metadata beyond what's stored in Iceberg file?
Can you repeat that?
Yeah, so the question was, does the REST catalog maintain any additional metadata beyond what's stored in Iceberg? Now, if you use the open source REST catalog, it doesn't provide any metadata out of the box, but I think the idea is that you can have a server implementation that provides additional metadata, right? And you can maintain, and it can be part of the same API. So out of the box, it doesn't, but you can extend. So I had the open API spec there that had maybe a dozen or 24 routes there. You can extend that and have additional routes without breaking the spec. And Iceberg client will just work in open source. An open source Iceberg client would actually work. Any other questions?
Yeah, thanks. Is there any concern with the scalability? Like if you just all of a sudden now just have we open it up to so many applications, is there some concerns about can this handle that many REST calls?
Yeah, so the question is, are there any scalability concerns if you open up the REST catalog to all these applications? There definitely is. I think there isn't for just typical like data compute engines connecting the way they normally would to like a Hive catalog or some other catalog. There aren't any performance implications there, but that is something to think about, that if you sort of open it and publicize it in the company and someone writes some JavaScript application that's sending thousands and thousands of requests a second, it could hamper the REST catalog. So I think that's always a trade-off where you have to look at the added value of whatever's being built versus the having to deal with that, which isn't really about data computation, right? And it's more of sort of an adjacent use case. Any more questions, or I think that's, we got one.
What is the REST server written in? Is it Python?
So the REST catalog itself is just a spec, but there's an implementation in the canonical Java Iceberg library. Yeah, and that's for implementing it as part of a REST catalog, as part of an Iceberg backend. But the front end, there's the Python client supports connecting to a REST catalog. The Java one does, of course, as well. And I'm hoping there'll be a lot more because that's another thing. It eases the ability to which you can develop a client in another language, right? And that's an interesting one, right? Because you know, I don't know if there's a Hive or you know, if there's a Hive dependencies that exist for like Go or some other language. But theoretically, if you're using the REST catalog, you can write a client in the language regardless if it has dependencies or if you're wrapping a Hive catalog. All right. Thank you, everyone.
So next speaker is Vikram from LinkedIn.
So I guess I'm the last speaker, so I'll let you go home early. I'll be short and sweet. Hi, my name is Vikram Bohra. I'm a senior software engineer at LinkedIn, and thank you, folks at Cloudera, for inviting me. Today I'm going to talk about how LinkedIn leverages Apache Iceberg to solve a pretty important use case. So let me begin by giving you a high-level overview of how data is ingested and compacted in our data lake. So data is ingested by a streaming pipeline from Kafka topics powered by Apache Goblin. Apache Goblin is an ingestion framework built within LinkedIn and open source later. So it's a streaming pipeline that ingests Kafka topics into hourly data, like hourly partitions, which is actually partitioned by the event time of the Kafka record. So this pipeline has very low latency, and it publishes the hourly partitions to both Hive and Iceberg. Now this landed data can contain duplicates due to upstream issues in Kafka and/or streaming due to failures on retries. Essentially, streaming gives you the same semantics as Kafka, at least once delivery, so your files can have duplicates in them. Also, it being lower latency, you usually have files of much smaller size. And in our data lake, we store our data for up to 2 years. So that essentially led us to build, the need came to essentially compact this data into larger files for storage and query efficiency. That's what gave the birth to compaction pipelines. These compaction pipelines operate on the hourly data. It actually deduplicates the data for correctness. It actually compacts data into larger files for storage and query efficiency, and it publishes hourly deduped and daily tables. Essentially, we have two flavors of compaction. One is hourly compaction, which publishes hourly deduped tables, and daily compaction, which publishes daily tables. For the remainder of the session, we'll be focusing on daily compaction. So this is how the diagram got a little thing. Okay. This is how daily compaction looks like. If you see, daily compaction today is a single shot MapReduce job that's actually compacting 24 hours worth of data from the previous day into daily data and then publishes the daily partition, right? All the daily compaction jobs are scheduled to run a few hours after midnight. Essentially, there's an assumption that the ingestion is going to finish sometime after midnight, and then and the compaction jobs are scheduled X time after that, assuming that the data has been ingested. It's a pretty simple model, right? But it has a lot of problems. What are the problems? As you could have already figured out, due to the single shot nature of the compaction job, the processing model itself is pretty inherently higher in latency. So, and as the data volume grows year after year, the publishing latency increases. And today we have latency of up to even 8 hours for very, very high volume data sets. The another big problem we have is there's no guarantees on data completeness. As you must have recollected from the previous slide, we just say, hey, ingestion must have completed by X amount of time, right? What if it did not, right? The compaction will compact whatever was ingested, whether it was complete or not, right? And any kind of late data that arrives after compaction causes a full data dedupe. That is, we call it recompaction, right? And essentially because of this processing model, we have another big problem, that is compute. I don't know why these are much more bolded than they should be, but okay. So as you can see, the chart here, this is the chart of our cluster memory for the queue on which the jobs are running. If you can see between the times of 1 a.m. to 8 a.m., you see those 3 big spikes. These are the spikes in memory that are caused by the compaction jobs. So what essentially does this mean? We have increased CapEx and OpEx costs of our compute clusters because the cluster is provisioned for peak resource usage, and our peaks are very high because of these jobs. And if you can see on the remaining, the left and the right hand side, we see a well below the guaranteed memory. That means we are underutilized a lot of time, right? Also, one more thing I wanted to mention is we have these, the peaks are actually like 3-4 peaks. The reason being all of our data sets cannot be compacted at the same time because they would essentially there'd be resource contention between them. So what our SRE partners do is essentially bucket the jobs by different timings. So some of the jobs are scheduled X hours after midnight, some of them after a few more hours. And we just stagger the jobs in order to make this happen. And essentially that increases the latency even more, right? So how can we make things better, right? I did speak about not being able to distinguish between late data and on-time data. That's the one thing we try to tackle this in the new model, is where the source data, we actually tag the data based on whether it's on time or late. Once the data is deemed on time, it never changes. For a given hour, if we essentially tag data as on time, if it is 99.99% ingested from the source, right? And only then only late data can increase for that given hour, right? So we applied those clean contracts to our data. And how did we lower our latency while lowering the cost, right? And the idea is pretty simple. We dedupe in small chunks of data throughout the day, essentially trough filling. So we reduce the peak hour compute usage and distribute the compute during the non-peak hours. So here's how incremental compaction looks like. Essentially, it's a Spark-based and Iceberg-based dedupe job. Essentially, at the very high level, what we do is, as I mentioned, streaming writes hourly partitions into the source Iceberg table, right? This deduper essentially is reading the snapshots of the source Iceberg table incrementally. Essentially, it reads from a previous saved snapshot to the latest snapshot. It dedupes the data, writes it to an Iceberg table, and then saves the latest snapshot in the state store to be used in the next one. So it's essentially building the daily data throughout the day rather than few hours after midnight, right? And to go even a little bit deeper, based on, since we are tagging the data as on time and late, we know at a particular time that for a given hour, the on-time data is fully been ingested. So in Spark, there's an optimization. It's a simple MapReduce job where we call dedupe on a few columns. And then we only need to, essentially, in order to dedupe late data, we need to know if it's already been present in previous hourly partitions. But the thing is, late data is just a tiny fraction. So we use the incremental Iceberg API to read the late data. And then we dedupe against already deduped partitions. So the join portion of our job is a tiny fraction now. Now, let's see how the graphs look after this change. So on the left-hand side is the chart we already saw. On the right-hand side, you can see that with 50% of our data volume onboarded, the peaks are no longer there. It has been distributed throughout the day. The latency has actually come down from 8 hours to 2 hours. And there will be fewer SLA misses during job failures because we are already checkpointing the last snapshots. We always have to process less amount of data in the last run. This significant reduction in operational overhead because we no longer need to stagger the jobs. All the data sets can be run around the same time. Now, putting this all together, this is a graph of our absolute cluster usage. So if you see the higher peak graph, the compaction jobs from the old compaction can use up to 30% of the overall cluster at peak. Whereas with the new model, we are at 5% with 50% volume. So we would be at like 10% when fully onboarded. So it's close to 15% reduction in overall cluster usage, being conservative. And by doing this, we have got close to 12% machines freed up on each cluster. Yeah, that's about it. Thank you.
So let's open it for a Q&A session. So Vincent, come up, and also we have Sam going to come up, and just so this is a Q&A time. If you guys want to ask speakers some questions, when you please, and the Shaun. So this is your opportunity to ask the speakers question. Yes.
You guys talked about the security integrations through Ranger. What about from a governance perspective? We have Atlas and Cloudera. Is there any extra work to be done to integrate with Atlas, or just because of the Hive and Spark integration, we'll get that for free?
So the question from audience is that is there any Iceberg integration with Atlas? Yes. So the compute engines that we have already integrate with Atlas, so that you will have a lineage governance type of capability as well. So the one that we shared in the demo is talking about the fine-grained access control, which was the compute engine integrated with Ranger, so that also working with Iceberg table. So we did a similar integration with Atlas as well, so that you can show the not only the security, but also the governance and lineage as well through the Atlas integration. So very good question. Thank you.
So in one of the slides, like it was Vincent view, so you mentioned about the compatibility of Iceberg with like public cloud, like AWS and all. How does this Iceberg look when it comes to compatibility on Ozone? Because as you know, like Cloudera is also pretty much pushing on Ozone. So what do you see in terms of compatibility with Iceberg and Ozone?
I want to repeat the question and.
So the question was on compatibility of Iceberg with Ozone. So we are working on integrating Iceberg with Ozone currently. And Ozone supports a Hadoop file I/O, and Ozone also has its own native APIs, interfaces, and it also supports S3A APIs. So all our Iceberg integration is using Hadoop file I/O, so that we can better integrate with the Ranger and Atlas and other components. So we'll be integrating both with the Hadoop file I/O, and also we'll also look at integrating and leveraging native Ozone file I/O, so we can avoid an extra hop if we can, and that can increase the performance as well on Ozone layer. Does that answer your question?
Sure, thank you.
Any other questions?
Yeah, a question about the REST catalog. So it is the expectation that we would be able to, let's say, have the REST catalog be the point of entry, and on the back end there could be Hive Metastore, or it could be some type of glue catalog or any of the others. So are we trying to like standardize on a set of APIs? And if we want to standardize on the set of APIs, then should there be some consultation with all the different packets?
Yeah, so the question was the REST catalog, and is one of its purpose sort of consolidating the different implementations or the different APIs of the different catalog implementations. I think that's a goal of it, but and there are, I think on the client side, the idea is it's interacting with the REST catalog, and that contract is always the same, right? But then what I think the other side of that are the adapters between the REST catalog and the various different underlying catalog implementations. So yeah, the idea there is that there will be different adapters for different underlying catalog types, so that essentially taking whatever the current catalog implementations that exist and mapping them to the REST catalog to allow really the exposure of that unified interface for clients. But is it the main goal? I don't think I would be the best person to declare that. Did I answer? Yeah. Okay.
Any other questions?
A question like, I think when you demo, when we convert the table to Iceberg, and when we repartition the table in Iceberg, so does the operation only affect maybe metadata, so the time and cost is kind of minimal? Is that the correct understanding?
That is absolutely correct. So in the in-place table migration, the demo that we did is so. Oh, sorry. You're all right. I violated my own rules. So the question is that just the metadata being rewritten in the in-place table migration. So yes, in the in-place table migration, especially when you're converting from Hive external table into Iceberg table, the only thing that being rewritten is just the metadata. If we change the metadata of Hive external table into Iceberg table, and we're not touching any of the data file itself. So once the Iceberg table metadata is being generated, we're pointing that metadata into the original data file that was actually coming from the Hive external table. So by doing so, number of advantages. Think about your petabyte size data, right? Netflix actually already talked about 100 petabytes of data sets. And if you want to retouching those data files, it's going to take a very long time. But if you're just regenerating the metadata files, very, very fast. So this is actually what we're recommending customers to actually, when they convert from Hive external to the Iceberg table, that's our recommended way of doing that. So very good question. Thank you. Any other questions?
I think it's for Sam and Vikram. From the query engine side, SQL consumption database side, what engines are being used at your deployments? Like in the example you gave, what's the query engine after your 90 jobs are complete? Or what's the set of query engines in place?
Okay, I think the question is, what are the query engines are used after the data has been generated? Yeah. So at LinkedIn we have Trino, we have Hive, and Spark is used for reads as well. So yeah, these three are the primary. I think Hive is kind of being phased out, but I think Trino and Spark are the primary reads.
Yeah. Spark, Flink, and Trino. That's it. But we also have a similar, taking streaming directly into Iceberg tables is a big one. So there's a lot of integration with streams. Yeah.
So actually, I think Vincent, maybe in his slides already highlighted one of the integrations that we're focusing on in his slides is that really integrating with NiFi and the Flink with Iceberg, so that you can have streaming ingestion into Iceberg directly. So this is one of the focus that from Cloudera as well.
Yeah, it's still streaming on LinkedIn.
That's the Zoom.
Yeah, that's the Zoom. I have one question, again, I think especially for folks non-Cloudera, is in terms of your adoption of V1 versus V2, what is it, what are you guys using right now?
So the question is, what is the adoption of Iceberg V1 and the V2 at the LinkedIn and the Netflix? So I will let maybe LinkedIn talk first.
We're still on V1.
Still on V1.
No,
Yeah.
LinkedIn. Is there what's I guess the question is okay, sorry. What are kind of your plans, or what are you waiting for? What's kind of the
more use cases? So most of the applications right now for Iceberg are compacting only files. but as soon as we hit cases like building, purging, capabilities or deletes, we're gonna start reusing these one that we deliberately.
So the follow-up question to that is when to use V2s. And of course, we all know that what's in V2 is row-level deletes and updates. So the answers from LinkedIn, as soon as there's operations for row-level deletes and updates, they'll adopt the Iceberg V2. So any Netflix?
Yeah. So I wouldn't be the best person to ask on like what the ratio is, but V2 is supported. So there are V2 tables that exist. I think if I remember, a big concern is it supported across every engine. So I know Trino recently has been doing a lot of work to add support for V2 tables. So that's probably the limiting factor on adoption. But I don't know the actual exact numbers of V2 versus V1 tables.
Thanks. So it's my turn to ask questions. So a follow-up to that is, what is your frequency and the concurrency of writes that you are expecting in your deployments? So the question to Netflix and LinkedIn.
Can you repeat the question?
What is the anticipated frequency and concurrency level that in your application deployments or your customers are communicating to it as a business need?
So are you actually referring to from the read side or the application itself?
From the right side. From the right side.
The application writing to Iceberg?
Yeah. Do you have scenarios where you have a concurrent reads and writes? And if so, what is the concurrency level that you are anticipating in your?
Okay, so I think at least in the application that I described, like we are reading from a different Iceberg table, right? And we are writing to a completely different Iceberg table. Yes, we do read from the destination Iceberg table, but that's within that application. But it's not concurrent in any way.
Okay.
So we just use it, like pull the data frames in memory to do the join, and then we write it out. So there's not that kind of concurrency happening, at least on my side in this application.
What about the write side? On write, like, do you have a lot of concurrent writes to Iceberg tables?
To the same Iceberg table?
To the same.
Yeah, to the same.
No, right? Like it's like one data set being processed as part of Spark, right? And then there's one execution, the writes happen, and then the execution happens again with the new set of data, and then the writes happen for that. It's not like multiple processes are writing to the same Iceberg table.
Okay.
I would say similar, but also I think the concurrent writes are probably not as much of an issue as concurrent commits. So the writing can be concurrent, but there's especially when we're doing like with the write audit publish pattern, like having to do you can get duplicate commit exceptions if you're doing commits for different separate concurrent writes to the same partition as well. So I think I don't know the numbers on like what's the level of concurrency that there is, but I think concurrent commits to the same partition is probably the most challenging area.
Maybe a follow-up question to Vincent. So like I believe you might have also evaluated some other things in the market, like Delta data. So what was your key data point to move towards Apache Iceberg?
So sorry. I think let me repeat the question. So Wala, if you can come up, and so Wala from LinkedIn as well. So I think the question is that what make LinkedIn actually pick Iceberg table versus other tables format out there?
Yeah, I guess the answer is simple. It's the most open table format and well supported by the community. So we're a community-driven company. And we believe that with collaboration with other partners in the community, the table format would grow. And yeah, we can influence the project and benefit also from other contributions.
Thank you, Wala. Any other questions? One more thing that what I like to do is also I want to introduce Christine. So Christine is actually she is going to devote herself as a Iceberg doc writer for the open community. So this is something that she's looking forward to work with everyone, all the Iceberg contributor out there, and she's looking forward to be a doc writer just for the Iceberg. So thank you, Christine. All right. So, all right, I guess the session's over, and thank you so much for joining in person and the folks that are logging on remotely. And we do have some, snacks, pizza, water, drinks. Please join yourself. Thank you.
Okay.